Good afternoon, all participants. Today we will start our session, and it's hands-on. So I'll introduce with the speaker of today's session. So it's my pleasure to introduce speaker of our today's session, Dr. Shishendu Roy. So it's Dr. Shishendu Roy has received the BE and ME degree in Electronics and Telecommunication Engineering from Indian Institute of Engineering, Science and Technology, Shibpur, India, in 2010 and 2016 respectively. He was with the Aditya Birla Group and CPP Automation Department, Hindalco Industries Limited, for 4 years. He has earned his PhD degree from the Department of ECE, National Institute of Technology, Rourkela. So during the course of PhD, he was broadly researching in the area of VLSI signal processing. He has published 3 SCI international journals with very high reputed publishers like IEEE Transactions and IET journals. He also authored a reference book on advanced digital system design. Several online tutorials on digital system designs are also authored by him. He is also the reviewer of many reputed journals like IEEE, IET, and Springer. His current research interest includes compressed sensing, FPGA-based implementations of algorithm like signal, image, or video processing algorithms, machine learning algorithms, artificial neural network, etc., low power architecture design, ASIC application of FPGA for IoT applications. Today, sir is going to give hands-on session on implementation of basic digital blocks on FPGA. So thank you, sir, for your time and effort. So over to you, sir.
Oh, thank you. So today,
Sir,
what
you
I
can
will
go.
do, yeah, today
Sir,
what
you
I will
can
do,
audible, sir. You can
yeah,
continue.
today what I will do, I will we will try to simulate some of the blocks, uh, like basic combinational blocks or basic sequential blocks, which are required in our in implementing any kind of algorithms, whether it is machine learning algorithms or signal processing algorithms, any algorithm, we need this basic block. So basically, a machine learning algorithm can be implemented by model-based techniques like using MATLAB, using Python. So uh, generally, if you go for this model-based techniques, so what will happen? The circuits or architecture what you get is not optimized. So we generally have less freedom in model-based implementations to optimize a circuit in terms of frequency, in terms of area, in terms of power. We don't have that much freedom in model-based techniques. So uh, we generally prefer that custom design of these algorithms. Custom means we have to implement this kind of algorithms in the by the means of this basic blocks like adder, multiplier. So morning also we have seen one lecture on multiplier accumulate block, that is MAC block using RAM. So this MAC block, what it does actually addition, and or it can we can say that addition and multiplication together it can do. So this MAC block we can do by the help of the basic blocks like adder or multiplier. So if we design the architecture by implementing these blocks by our own Verilog codes, then gradually we will have the more freedom to optimize the circuits in terms of power, frequency, or area. So today we'll focus on some of the basic blocks, and I think day after tomorrow also I have a session. So in that session we'll try to implement at least one architecture of machine learning in the Vivado, and we'll try to implement on the FPGA. So first we'll learn the basic blocks, and with the help of basic blocks we'll try to implement that machine learning function on the day after tomorrow. So what tool we will use? We'll use the Vivado tool, and currently I'm having Vivado 2019 version. So, and the language in Vivado you can use either System Verilog or Verilog or VHDL. So recently, Vivado has this System Verilog thing. System Verilog is very useful for industry, we know, and also Vivado has the Vivado HLS part. So Vivado HLS also we have, where we can design the systems using the C or C++. So again, the HLS is a high level synthesizer where we write in terms of C language to simulate the uh, basic algorithms. But today, what we will do, we'll try to take the help of basic Verilog language, and with the help of Verilog language, we'll try to implement some of the major blocks. And if we have these major blocks, or we will know the major concepts, then we can go for the implementation of at least one machine learning algorithm. Say, I can say we can implement one activation function, like we can implement one sigmoid or hyper or tanh function, or we can implement a softmax function that we can we'll see in the next day. So today we share. So uh, is the screen visible?
Yes, sir, visible now.
Okay. So today this is the test project I have created. I will go very slow. I think most of the participants know this how to use Vivado, but again I will tell so that it will be a refreshing also before going to the final implementation of one topic. So here, the first thing what we do in the Vivado is that we go to settings and we choose that what target language is that. This is the first thing that we do. So here is the target language is Verilog. So if you are using System Verilog or Verilog, our target language should be Verilog. If you are using VHDL, then target language should be VHDL. And from here, you can choose the project device, that is the FPGA device. So what we will do, we'll choose one known uh, board, that is XT100 XT100T. Okay, this board, which this board I have used many times, so I will use this board. This is a very good board. So I have selected the board. I have selected the language. Now apply and then go to okay. So now our first part is done. That is target board setting, and our language is fixed. So now what we will do, we have many kind of sources here. So first is design sources. In the design source, what we will do, we write the main Verilog codes. That is the design module we will write in the design sources. Then we write constants, that is FPGA connections, we write in the constants part. We write the simulation test bench in the simulation part. So first of all, in the design sources, we will do add source. After add source, we will create a design source, add or create design source. Here, we'll create a file, and here also you can choose language or what you want to do. You want to do a Verilog code only, Verilog header, system Verilog, VHDL or memory file. So here we want a simple uh, Verilog file for first block. This is called adder subtractor. So this is the first block that we need called adder subtractor. So every kind of algorithm, whether it's machine learning or filter, every kind of algorithm should have a adder subtractor. So adder subtractor block means it can do adder addition or subtraction based on the control signal. So we will choose this block first and just create it. The spins we will do later. No need to set up here. Okay. So now this it came here. Double click on this block. Now here one module is created. In that module, what we will do? I have some ready-made codes that I can paste here. So first, for the first code, what I will do, I'll write it as a okay. Now what we have to do? So adder subtractor has one input called select. So I write it here input select. Okay. So first block I will do by myself. Second block I will copy the ready-made codes. So adder subtractor has one input called select. Based on that, it will do addition or subtraction. Now it will have other inputs uh, like A and B. So I will take 18 bit. I will take 18 bit as a two 18 bit I have taken. So A and B are the inputs of the adder subtractor block. So based on the select line, it can do either A minus B or A plus B. So I can simply write this module as assign output. Output is S is equal to, I can write as a, in the bracket, I can write select, can write here uh, A minus B or can write A plus B. So what I have written here, this entire code is written as in the conditional conditional way of writing in Verilog. So it's very simple. If S is one, it will perform subtraction. That is A minus B. If if select is zero, it will perform as A plus B. So when select is zero, it will do the addition. When select is one, it will perform the subtraction. So now last part is pending, that will define the output. So it will take us output 17 minus 1701. Yes. And finally, I have to define all the input output in the under the parenthesis. So select, I have input A, B, and S. So here, the complete code of the adder is done. So we have a control signal called select, input A and B, output is S. So generally, in adder subtractor, we have another input called the carry out. But if we are interested only in the bigger system design, so we generally avoid the carry out signal. So our addition or subtraction result should be restricted to 18 bit. It cannot exceed the 18 bit. Okay. So now our code is done. But what is important here that my architecture can be either 18 bit or you can say 12 bit or 10 bit or 24 bit or 32 bit. So every time if I use this same adder subtractor block, I have to change this parameter 17 is to 0. But what we do to make a general kind of block, we have to design this block such a way it behave like a general. So what I will do, I make it, I will take help of one parameter. So I write as a parameter n is equal to some value. So initial value is 18. This is the initial value I am giving 18. And so based on this n, our width of the inputs and output will be controlled. So I can write this here in terms of n minus 1, here also n minus 1. Now, in the main design, if I call this error subtractor block, then what will happen? I can just change the value of n, my entire width of the inputs and output will be changed. So it can be used in a as a general kind of block. So this is done. Our design is completed. Our design is n-bit adder. So name also you can change it at sub n. Now we can next job is that I have to make it a I have to simulate it. Okay. So for simulation, what we will do? We have to go to simulation sources, write a another simulation source. So when you are designing a Verilog code, you have to write design source. When you are simulating, you have to write a simulation source. So I will do simulation. You can create a file. You can say add sub underscore t. Now, in the simulation sources, generally, uh, every time what I do, this is a practice I make. Every time the file name, I start with the end with the underscore test page. So you can differentiate between the main design and the test bench design. So this is a general practice I maintain. You can have your own convention. So now this is the so one test bench is created here. This is the at sub NTB. So here you can see this is the test bench created. So now I write this test bench also. Okay. Now in our design, what are the inputs? Input is select and A and B. And we know that inputs and inputs are going to be raised in the test bench. Why? Because uh, they are going to be in the always loop. So rage select rage 17 down to 0 A comma B, and what is output? Output is becoming wide here. Output is 17 down 0 S. Now I have to call this block, entire block I'll call because uh, I have to give test bench to this module. So I have to call this module. So I will copy this module and paste it here. And so it's a general uh, module. And in terms of parameter in, I can put here n equal to 80 and put it here UUT, unit under test. So see here, I put here 18 because I have used here 18 bit, 18 minus 1 colon 0. I can give any number here. I can give here 10 also. I can give here 5 also. I can verify. So as of now, I give here 18. Now inside the initial begin, I have written, I have to write the inputs. Like what is the first select? Select should be your initially 0. Then I'll give A. Inputs I can give in terms of decimal also, in terms of hexadecimal also, or binary also. So what I will do in terms of decimal, we give here tick T9, P tick T8. Okay. So now the simulation test bench is written. The next thing we have to go back to the sources and we have to simulate the test bench. Now in Vivado, if you are simulating one test bench source, that test bench should be top level. That means you can set any test bench module to top module by clicking here. and selecting this as a top model. Okay, so this is already as a top, so no option is coming. But if it is not there, you have to make it as a top model. So once it is done, you can just click on the run behavioral simulation. Okay, so now here you can check. Now here one very important thing is that the results are coming in the decimal or binary, whatever it is. You can change it to any radix. Just select all, make right click and change the radix. So you can take it as a signed. So you can see 9 plus 8 is 17. Let's uh, take the negative also. So what we will do after some time delay, we'll vary the input. So I'll give as a 100. So what does it mean? 100 means 100 unit delay. 100 unit delay. So what is the unit here? Unit here is the nanosecond. So 100 nanosecond here. So it is a 100 nanosecond delay. After that, we'll change the output. So what I want to change? A and B I will not change. I will change only select. So select I am changing here. I will make it as 1. So now it will do subtraction. It must do subtraction. So here, once you did the modification, do not again go to the run simulation. This is the generally uh, mistake we do. After changing, what we will do, go to the test page, outer simulation window, and click here. It's called the relaunch simulation. So whenever you are changing something in the test page, do not again run simulation. Just click on the relaunch. It will give you the new value. So now you can see here what is our subtraction result. So when select 0, it is doing addition. When selection input is 1, it is doing subtraction. That is 9 minus 8, it is 1. Is it clear? So I hope this basic simulation, uh, I think all of you know. Just I have shown you this adder subtractor. But what is important in this simulation is that we have to write every code in this manner with the help of parameter so that we can change the parameter anytime in the design. Okay. So this is very, very important. This is the fixed point at a subtractor we are doing, and we are avoiding the carry, avoiding the carry out. That is no need of considering the carry here. So this is the major block that is used in many cases. So accumulator is used in ANN, CNN everywhere. So we can take all help of this add a subtractor and make a big accumulator. Okay. So what is the next important thing that we should know? Next important thing we should know is called the multiplier. Next important thing we should know is called the multiplier. And multiplier is one of the important module in the implementation of algorithms, any kind of algorithms. So what I will do now, I have the ready-made code here. I can do okay. Uh, multiplier code we can easily copy from one side and multiplier code we can do where we have it. So here I'm writing in the same same Verilog source code, that is add sub n, but module name I am giving different. So it's also good practice to have all the basic blocks in single Verilog module, so that everything will be in the single thing. And what you can do, you can minimize this code, everything you can minimize. Yeah. So now I'm focusing only on the multiplier. So here, multiplier, we have to understand importantly, that there are two parameters in the multiplier, which is one is called n, which is the data width. N is the data width. What is precision? Precision is very important thing here. So precision means that how much accuracy you want from the multiplier. Like you can say, if I use two 18-bit input, if A and B are both 18-bit, what will be the output width generally? Output which will be of 18, not 18-bit, it will be of 36 generally. So 36 bits should be, if I use 18 bits input. But I cannot take 36 bits, because if I place another multiplier after that multiplier, so then 36 will be 72. Then it will increase like this. So I have to make it a make some compromise here. I have restrict the output to the 18 bits. So what I have to do, I have to define some accuracy. What accuracy I need here? So here uh, you can give accuracy like 10 bits or 9 bits. Okay. So what I choose here, I choose here, suppose I need here 10 bits of accuracy. That means you have to 10 bits of accuracy means total 36 bits will be there. You have to remove 10 bits, remove 10 bits from the LSB side. So if you take 10 bits from the LSB side, so now uh, if you calculate, so what is the starting bit you are taking here? Starting bit should be your starting bit should be 10 from the LSB side. Now you have to take 10 plus 18. What is 10 plus 18? You have to take 27 to 10. So 27 to 10, if we take, it will be 18 bits. So you are removing some bits from the LSB, some bits from the MSB also. So together, we are only taking 27 to 10 bits. That is 18 bits from the middle. So this way, we are designing the multiplier so that output will be restricted to 10, only 18 bits. 18-bit multiplier means 18-bit output. So accuracy of the multiplier depends on the precision you are using. If you are using precision of 9 bits, you will get less accuracy. If you are using more like this 12-bit accuracy, 12-bit precision, you will get more accuracy. But the problem is, if you are increasing, if you are increasing precision means lower range. Because if you are increasing the precision, how many bits we can accommodate? We cannot accommodate a high range of multiplication. So if you're increasing the precision, your multiplication range will be less. So this is a very simple multiplier code here. You can see P is equal to P1 is equal to A into B. This is a simple multiplication. So this is the, you can say, 36 bits. But is P is 18 bits. Okay. And so if you understand this block, you can easily simulate this block also. So what I will do, same test bench I will do and modify there. Uh, add sub n is the block, and I can write yeah. I will modify this code only, or I will write a separate code. Toggle comment content. So we don't have select here. We have A, B, and S. So here, what is the name of the module? Mult-in. Mult-in is the name. I write here mult-in. What are the parameters? I have two parameters here, as I told you in a multiplier. One is n, another is precision. What precision I want? A precision I want is 10. Okay. So here, select I don't have. So input A, B, and P. Okay. So say S is the output. Select I don't have here. So I will just remove this. Yeah, my test bench is ready. I can go back. Yeah, first, this simulation I'll close. Okay. Now my simulation name is multntb. Okay. I can do again simulation, run behavioral simulation. So we got this simulation here, but in the multiplier, we have to understand the simulation very, very importantly, because unlike adder subtractor, multiplier simulation is very, very important. And if you see here, if I make it to signed decimal, to see what is the result coming. 9 multiplying and 9 with 8 multiplying. What is the result coming here? 0. Is it correct? I am multiplying 9 with 8, but I am getting 0. Is it correct? It is actually the correct answer. As per the binary rotation, it is the correct answer we are getting. 9 into 8 will get here 0, because this 9 is not exactly 9. It is the fractional. That is, it will be maybe very, very uh, less than 1. 8 also is less than 1. So here we're getting very less value that is not possible to represent by the 18 bits. That's why result is less than uh, 0. Okay, we cannot accommodate the result here. So try to understand it better. I write the test bench in a better way. So what I will do to understand this test bench better, I will take 18 bits data and 10 bits precision. So now I will write this A and B. I will take 9 and 8 only, but I will take 9 and 8 in the fixed point representation. So what is the fixed point representation? Some bits will be for integer, some bits will be for fraction. So I will use 10 bits for the fractional part, because precision is the 10 bits. I will use 10 bits for the fixed point representation. So how to write 9? So I'll take 18 tick B. That means 18 tick binary. B for binary. So 9 means how many bits for integer? 8 bits. So 0, 0, 0, 0, 4, 0, 4, 0, then 1, 0, 0, 1. Then this is called our 8 bits. After that, we have fraction, but we have no fraction here. So 0, 0, 0, 0, 4, again 4, 0, then 2. So we have total 18 bits here. 2, 3, 4, 5, 6, 7, 8, 9, 10. Here, you can give it in the heads also, but you have to calculate. But for to understand it better, I'm giving in this way. Now I need B also. So B I have to give 8. B, I'll give it as a 8. So this is 8, this is 9. What should be the result we got? What should be the result we should get? Result we should get 8 into 9, 72. What is the binary of 72? If I calculate, the result should be 72. So 72 means you will get here. Okay, let's see the result, whether it is 72 or not. So I change the, I relaunch the simulation again. Okay. Now here I got 73,728. So by seeing only the result 73,728, you can check that it is a correct result, because 9216 means 9, 8192 means 8. How? Let me explain again. So used I have used here how many bits of precision? Precision I have used 10 bits. So 10 bits precision I have used means 2 to the power 10 power of 2 will be coming around 1024. So my precision, that is 2 to the power 10. Okay, 2 to the power 10 is equal to 1024. Now multiply this number with your 1024. What you are getting here? This number. That is 9216. 9216. This is your corresponding number for 9 with 10 unit precision. What will be the B? B will be your 8 into 8 into 1024. That means 8172. 8172. So the result you should get 72. Result you should get 72. That means result should be 72 into 1024. It will come exactly like 73728. It will come 73728. Understood? So this is for precision of 10. Now, if precision is 9, so you have to multiply by 2 to the power 9. Here, now from the test bench, you got it 73,728. How to understand it is correct? Just divide this number 73,728 by 1024. That is 10-bit precision. So 73,728 divided by 1024 will be your exact result. Also, if you change it to radix binary, you can change 72, it is on or not. So here you check 8 bit from the MSB. So it is exactly matching. It is actually your 64 plus 8. 64 plus just exactly the, my pointer is noting the decimal point. Okay. It's exactly your 64 plus 8 is equal to 70. So now your multiplication result is very, very clear. So till now, any doubt is there, I can raise question because it's a hands-on session. So during session also, you should ask questions. I know many of the faculty already know these topics, but still, if you have any doubts, tell me, or we can go for the next block, because multiplier, adder, subtractor are very major blocks in uh, designing any kind of algorithm. Okay, we have finished multiplier and adder, subtractor.
Look, can you please repeat how to represent the number with precision 10?
Yes, okay, I'll repeat it. Okay, this is a very good thing. So we have used 10-bit precision, correct? So that means for fraction, we are using 10 bits. Okay. Now our number is 9. Okay. No fraction here. That's why these numbers, these 10 bits are 0. Understood? These 10
Yes.
bits are total 0. There is no fraction part. And this part will be your integer. That is 9. So if you see first 4 bits, these 4 bits are integer. That is 1009. In decimal it is 9. Okay. Similarly for 8. Now I give another example. Suppose you want to take b equal to 8.5. Okay. B equal to 8.5 I want. Okay. So I have written 8. Now uh, this underscore I have written here uh, by knowingly, because underscore denotes the decimal point. Underscore denotes the decimal point. So if you underscore, result will be same only. Underscore is only for the decimal point. So after the decimal point, if you give here 1, that means the number will be 8.5. That means uh, the weightage varies here, like 2 to the power minus 1, then 2 to the power minus 2, then 2 to the power minus 3, then 2 to the power minus 4, like this. Okay. So it's a 8.5 because I have here 1. So it is like a 8 plus 2 to the power minus 1. Now, if I add another one here, it will be 8.5 plus 2 to the power minus 2. That is 0.25. Is it clear? If I add another one here, it will be plus 2 to the power minus 2. That is 0.125. This way, you can represent. Is it clear?
Yes. Yes. Thank you.
Uh, Now, the general technique is that if you don't, because this calculation is little bit lengthy. Now, the what is the rule actually we follow? That what is the precision we have? 10 bit. So, what is the 2 to the power 10? 2 to the power 10. What is value? 10-bit precision, and 2 to the power 10 means 1024. Correct. Now, to know the binary value or decimal value of the 8.5, simply multiply 8.5 into 1024. This is shortcut procedure. You will get the decimal value and then convert it to the binary. What is the 8.5 into 1024? You can easily do. Is it clear?
Yes.
So simply if you multiply 8.5 into 1024, you will get 8704. Now just convert it to binary, or sometimes no need to convert it to binary also. Now, how to get back from decimal to binary? Like this is decimal number 9216. How to get back to decimal to this unsigned decimal to floating point? Divide by the 1024, because this is the precision. Okay. Okay. Now this multiplier is actually signed multiplier. So you can make it as unsigned also or signed also, based on the keywords. Okay. Basically, we use signed multiplier only because that is the only required thing. Okay. So next important block. Now I will not simulate adder subtractor and multiplier is done. Next, what is important block? Now we'll go for some sequential block. So sequential blocks, if I go, yeah, sequential blocks. If I go sequential blocks, okay, let me search it here. What is the most important sequential block? Is the any doubt? Anyone? Any doubt? Okay, so we'll go for most important block, that is called register. This block, try to understand. This is the another most important block that we use. So here I am writing here sequential block register. So now this block is very interesting block. This block we can use as a pipeline register. Okay, first of all, this block you can use to delay a certain signal. This block we can use for a D flip flop. So this block can do multi-purpose thing. Okay, So what is the need of this pipeline register? Let me, I think you all know, but this is actually parallel in parallel output register. So parallel in parallel output shift register, PIPO. PIPO is used for the pipelining. PIPO only is used for delaying signal also. Okay. So it is a very simple behavioral coding, always at the rate positive is clock. Okay. We can use negate clock also, positive clock also, but only one cannot have both positive clock or negate clock. Only one you can have. Now it is a if reset y equals to 0, else y equals to 8. That means reset is happening with respect to clock. It's called a, we call it as a synchronous reset. So generally, we follow synchronous only. Asynchronous we don't want to do because asynchronous creates a lot of problems in the uh, static timing analysis. So better to use synchronous reset only, but sometimes also we can use asynchronous. No issue because in terms of clock domain processing, we use asynchronous reset. Okay, so it's very simple coding. If reset y equal to 0, else y equals to a. Now it is synchronous reset, but also it is active high. That means when the reset signal is high, it will do the resetting. When the reset signal is high, contents of y will be clear. It's a active high also and synchronous reset also. So generally, Xilinx FPGAs follow the active high, and Intel FPGAs they follow the active low concept. Okay. So again, parameter is used here for every kind of coding. Use parameter. Okay. Parameter why are you using here? Because n equals to 1 means it is a D flip flop. Okay. If n equals to 1, it is a simple D flip flop. Okay. So if it is n equal to more than 1, it becomes a register. If it is n equal to 1, it becomes a simple D flip flop. So for multiple data which also you can use this register block. Okay. So I am not doing simulation here. One simulation should show. I show for the counter basically. So this is one of the important block that you should understand why the reg n is used. So let me show you why reg n is used. This kind of block. Let me see this architecture. This architecture is a parallel architecture, and here you can see before every after every input we have register phase. This register means this register which I have designed here. Now, how many data bit can be there in the A1, A2, A3? Based on that, you can vary the value of n. If A1 is 18 bit, you can put here 18 bit. If A1 is 2 bit, you can give as a 2 bit. Similarly for adder. Okay, this is a parallel system we have for calculating the mean. Similarly, we can see another architecture. It's called the pipeline architecture. It's called the pipelining concept. So this register block used for pipelining. So what is the objective of pipelining? Pipelining means to reduce the delay in the combinational path. So here, initially we have total combinational path of 3 adders, but we have reduced it by uh, of one adder by inserting the register in between the adder paths. Okay, this is the purpose of the register block. Okay, next block that is very important, which is the count. Counter, I will explain it very because counter is very important. I'll do simulation also for counter. Okay. So counter may be up counter, down counter, maybe a synchronous counter, mod counter, Johnson counter, shift register counter, many counters are there. But here, this counter I have designed is a multi-purpose counter. and this counter can realize the other counters easily. Okay. So this counter, try to understand. First of all, I have used one parameter. This parameter is very important because if you want to change the width of the parameter, this it can be any kind of counter. It can be 4-bit, 3-bit, anything. Now, mm, I'll explain with you another diagram that will be better. Uh, so this diagram is for the actual counter, but what I want some block diagram. Okay, so no need to explain from the diagram. Okay, let me check here. So first we have the synchronous mechanism here. If reset count is C, this is understandable. And we have a positive clock that is positive we have. Now one important feature is there. If load is there, any data that is input to the counter will be going to the counter. Okay? So if load signal is high, any data that is input to the counter will go to the count. Else, if enable is high, it will do the up counting. This is a very simple behavioral coding. And finally, we have to generate one terminal count signal, that is if always at the rate, if count is equal to limit, we get terminal count signal 1. This signal we can use in multiple purpose. Okay? So what we'll do, we just simulate the counter, then we'll understand it better. I write the test bench here only, the same thing, and I'll do comment on top this. Okay, so I write it here, count dot module at right now. Module count underscore TV will be input clock reset enable load. Then we have initial, begin, end. We have end module. Okay. One of the important part is the sequential block, which we have to define the clock. Always at the 5 clock is equal to clock. This is the clock, and then instantiate this count here. Okay. So what is the output? Output is your, let's say we have a 4-bit counter we design. So 320, output is count. Uh, we have many inputs, other inputs are also limit we have, and data. Data means which data you want to put, initially 0, and we can put any data. Limit means up to what the limit will, counter will count. So input means it will be range. It will be 3 down to 0 data and limit. Okay. Parameter, I want to make it as a 4-bit counter, so I will make it as a 4 UUT. Okay. Initially, clock signal should have a value, so clock is equal to 0 or no. Achha. Reset in sequential circuit. What is the most important thing is that reset should be initially 1. Reset should be initially 1. Then if this other signal you can give. Like I want to make reset signal 1 initially. Data also I want to make take the 0, and the limit I want to make it as take the say 9, and after some time I will make the reset signal 0, because in sequential circuit reset we have to make 1 to get the initial value to the flip-flop. Reset should be initially high, then after some time reset should be again come back to 0. So our limit is 9, that means counter will count up to 9. Now one signal we missed here called enable. Enable should be high, then only your counter will start. So next is load. We can make the load signal initially 0, and when required, we can again put it. So TC is the output. We can say where TC, where is the output. So everything is done. Now we can do the simulate. Now count TB already done. This is a simulation. Okay. Now here we can see the simulation. Clicking this and zoom. If you see, counter is counting 0, 1, 2, 3 up to 9. After and whenever it counts to 9, it generates the terminal signal. TC signal is very, very important. Whenever it counts up to 9, it generates the TC signal. This means this terminal count signal is very, very important to start other process or to stop other process. So TC signal is very, very important signal to control other mechanisms. Now see, I want to start this counter from certain value. What I will do, I will do one certain thing that let's say this load signal. I will take load signal here, 1, and data is equal to tick T3. So load signal generally it should be also a pulse. So after certain clock period, 1 clock period, I'll make this load signal again 0. So now load will be high for 1 clock period. Then this load signal will load this data to the counter and enable is already high. So what I will do, I'll again do simulation. Ah, Now if you see load signal is high and data was our 3. Data was our 3. So counter is starting from 3. Now it is not starting from 0. It is starting from 3. So starting from 3, counting up to 9. So we can say it's loadable up counter. It's a loadable up counter. But see, the counter is counting up to uh, counter is counting up to 15. Now this terminal count signal is generated at 9. Now with the help of this terminal count signal, we can stop this counter. So it will count up to 9. So we can make it as a mod counter. Anytime we can make it as a mod counter, whether it's mod 7, mod 8, mod 9, any kind of counter we can make with the help of this loadable counter. Okay. So loadable counter is very, very useful in kind of system design. So today we have discussed some blocks like adder, subtractor, multiplier, then register, then counter. Okay. Lastly, what I will do, I will just give a brief. I will not simulate it, but I will give a idea of memory blocks. Memory blocks is very, very important because without memory you cannot store anything. And there are two type of memories. One is ROM, another is RAM. In RAM also, so one article is here. You can easily go through this, or one article is there called memory design. So in memory design, we have uh, what is control register. Control register is for 1 byte storage. So you can store 1 byte of data in the control register. ROM, you can store particularly some data. You have random access. But most importantly, what is the important memory is that dual port RAM. So dual port RAM means we have a entire memory area, and there we have 2 ports. Okay, and from any port we can write, from any port we can read, and we have two output, D out A, D out B. One table is there here. If you see, enable A, WEA, enable B, WEB. So enable A and W, if all the signals are high, it will be right through port A, right through port B. If WEA is high, it will be right, and WEB is zero, it will be read through port B. Similarly, we can do read write, read read from this kind of memory. So dual port ROM is very, very important. Why? Because we need such a memory like that. From one port we are writing, another port we are reading. Okay. So one port I'll just try to show you here. It is yes. This is the code entire two dual port memory. This is called. So this dual port memory, if you see, uh, we have total data width A. This A, the data width, address is the 4. Okay. So address of any port is A. ADA, address of port A, ADB, address of port B, in A, data through input in port A, data through port B, enable A, enable B. Clock also differently possible. Clock A, clock B. Okay. Write enable A, write enable B. Output A, output B. So we have separate signal for different ports. So here it is simply given for one port. This is one port, and this is for port B. Very simple code. If enable A is high, or enable A and write EA, both are high to write. Okay, and if write EA is 0, then read. That means enable A high and write enable 0, then read. Simple, same code is for port B also. So generally, what we do, we may have both the type of clocks, or we may have same clock. If we are having same clock, then it's called synchronous. If we're having different clock, we call it asynchronous. You probably heard of asynchronous FIFO in your design spirit. What is asynchronous FIFO? Asynchronous FIFO is nothing but a simple dual port RAM where one port we are writing, another port we are reading. Okay, so dual port RAM is very, very important. Now, one of the important thing is that this part, initial begin read mem age initial dot text mem. That means what is done here through this initial dot, actually not dot text, it's a mem file, and it's a 2D array. 2D array here. This is the data width of each location, and this is this number of location. That is 2 to the power m minus 1. If m equal to 4, locations are 16 locations. So 16 location we are having, and each location we have total 18 bits. Okay, this is the 2D array. And now how to initialize the ROM or RAM? This is through the initial dot main. This file we have to create in the Vivado, and through this file we have to store the initial value, because we cannot store all the data through the case statement. We have to use some kind of memory file. How to do that? Go back to source, the design sources, add source, you go to the design source. Okay, we are dealing with the design actually. For design source, here create. Here you'll get one option called memory file. Yes. So instead of Verilog file, choose this option, memory file. Give it a name, initial. Same name you have to give, initial. Now here, one important thing is that memory file is created, initial created here. The extension command is read mem h. H means hexadecimal, B means binary. So you can give it hexadecimal also, you can give it to binary also. So you can give it like any number. You can give 0, 3, if E or G. Like this way, you can give the numbers. Okay, this way you can give the numbers. So you can just copy 16 number here. Okay, you can copy 16 numbers here. So automatically the memory location, the 2D array name will be loaded by this initial bin value. So you can use this memory anywhere in the design. Now, for loading data permanently, we should use ROM, and for reading and writing, we should use uh, dual port RAM. Okay. Now, what is the use of dual port RAM? Dual port RAM has many kind of use. Suppose you are doing some kind of compilation on your network. So see, layer by layer, we have to implement. That means after input layer, some data should be temporarily stored in some memory. There we have to use dual port RAM. After that second layer, we have to store that value there. After the third layer, we have to store that value there. This way to proceed. It's not like you can, without using memory, you can do the compilation unit. It's not possible without using memory. We have to store the data. Now, what is the use of ROM? Initially, if you want to use, if you want to verify a CNN, so that CNN should be verified by your existing data, not coming from the real time, real world. That data you can store in a ROM and you can feed to your CNN design. That time you can entire image should be stored in a ROM. That is permanent. Okay. And then ROM should be used for your mm, weights, weights that you got from the training. That weights also you can use in the ROM. Okay. So today, up to this, we will discuss the rest. Next day, we will try to simulate one entire block, either a activation function or some regression algorithms, and then we will try to make it as a IP. Okay, that is our target in this hands-on session. So I like to finish here. If any kind of question is there, please let me know. I'll try to clear. Any question from the participants?
Excuse me, sir.
Yes. Yes.
So when you are storing the intermediate results in the memory or in ROM, so while accessing all those data, we have to put it in a for loop and we'll be calling those values filter wise.
Let me tell you. Okay. Intermediate data, suppose from one layer, you have to store in a RAM, not ROM. Okay. So that's why we're using on dual port RAM. Okay. What we will do, uh, to one port, you're writing all the values to the RAM. Another port, simultaneously after one clock cycle, you start reading also. Okay, this is the best way to do. So you are writing through port A, and after one clock cycle, you can start simultaneous reading also from that memory. Okay, it will save your time. That's what we're using dual port RAM instead of single port RAM. Understood? And for your example, you are telling us how to read from a layer training.
Yes, sir.
Reading from a layer means it should be output of a some block, no? Suppose accumulator or something, no? So accumulator output directly can be connected to the your memory. Like for example, in the first layer you're using ReLU function, correct? So ReLU function output should be directly connected to the memory, to the memory. Clear? And how to write the data through some counter. So in memory, there will be some counter. That counter will give the address to the memory. So that each value will be loaded to the memory. Okay.
Fine, sir. So while when fetching the data also, we have to follow the same procedure
Yes, with the help of some
to a
counter.
counter.
See,
Okay.
what we write actually, basically, maximum students, what they do, they combine so many behavioral codings in a single code. So basically, they are writing some for loop, which is not recommended. Ultimately, what they're doing, you are using a for loop means it's a simple counter only. If you write always at the rate something I is equal to I plus one, so it's a counter only. You are using counter only, but together you are merging in a single code. It will be difficult for troubleshooting. Understood? No?
Acha. Right, sir. So if a residual connection will be there, then some previous data we have to, let's say, take it out from um, like layer by layer. If you are feeding it, then as you said, ki, like output will be going to the next layer through a dual port RAM. We are feeding it and we are taking it out. If you are having a residual connection or something, some
Like I'm just telling, suppose I don't know what you're learning, but what is I'm saying is that suppose you have three layer, okay? Suppose you have three layer, first layer, second layer, third layer. But the first question what we are facing in implementing this CNN or like this is that the area cannot have so many layer parallelly implemented. So generally what we have to do, we have to take one block and that block we are using recursively. That time, previous contact, previous value of the data in the memory will be gone. Again, you write new data. This way you have to proceed, like in a loop.
right, sir. So we can having that for a residual connection. That's what like a previous data which you have stored
Uh,
that you have to again further process it. Then it will be not possible.
yes,
Because
it's a
only a
temporary
sequential
memory. No?
flow we can. Right. Only a
You
sequential
have to
flow we can.
see. You have to see that that data is required or not. If it is required, you have to store. If it is not required, you can I mean uh, change it.
Okay. Right, sir. Okay, sir.
Any other question?
Participants, any questions? I guess no questions, sir.
Load means somebody asked that load means we are loading some value to the counter. That means from what value the counter will start. Suppose you want to start the counter from 3, so you give a load signal. You want to start the counter from 9, so it will start from 9. That time you have to give the load pulse. Okay. Any other question?
Any other questions, participants? I think no more questions, sir.
Okay.
So thank you, sir, for your insightful talk. And we request participants to be there at 4:30. So for tomorrow's session, Dr. Shiv Shankaran will join to tell about how to install the software, because many people are facing problem. So you can join at 4:30.
Thank you, ma'am. So I can leave.